In this video, we're going to talk about parallel circuits. This is an example of what a simple parallel circuit looks like. You've got a source with two or more loads. It's different from a series circuit. In a series circuit, there was just one loop, and all the resistors were on this loop, and all the electrons went through all the resistors. In a parallel circuit, you get branching, so that some of the electrons come through one load, some of the electrons go through the other load. So like the last time, I'm just going to put numbers to this and talk about the relationships and how to solve something like this. So we'll just use the same numbers as the series circuit example. 10 volts at the source, R1 2 ohms, and R2 is 3 ohms. Okay, now you should have seen when you looked at combinations of resistors that if you've got two resistors in parallel, the relationship that governs them is that 1 over the equivalent parallel resistance is equal to 1 over the first resistor plus 1 over the second, and just as many terms as you have resistors. So let's start by just solving that, because we're going to need that. So 1 over R parallel is 1 over 2 ohms plus 1 over 3 ohms. These are nice numbers where you can get a common denominator. Your textbook, a lot of them aren't this nice. So we'll take as our common denominator 6 ohms. So 1 over 2 is 3 over 6. 1 over 3 is 2 over 6. So 1 over RP is 5 over 6 ohms. And now to solve that, you have to flip both sides. So RP over 1, or just RP, then is 6 ohms over 5. This is the step people often forget, the flipping. That's 1.2 ohms. The basic approach to this is the same as with series circuits. Is we're going to set up a chart, and we want to know V, I, and R for all the elements in the circuit, so for R1 and R2, as well as the total for the circuit. And we'll write in what we were given. We know the V of the source, that's the total potential for the circuit. And we were given the two resistors were 2 ohms and 3 ohms. Now we also have calculated that the total resistance is 1.2 ohm. So this total is not an adding type total, it's the total effective resistance of the two resistors. Now it may seem counterintuitive to you that the effective resistance of two resistors is less than each resistor individually, but that actually will always be the case. It's a lot easier for electrons to get through a parallel circuit because now instead of just one path to take, they've got two paths to take. In your skiing analogy, it's like if you opened up another ski hill and then the skiers could go down the first hill, but now they've got a second hill. Well, they can get a lot more skiers through. Well, the circuit can get a lot more electrons through, and therefore the overall resistance is less. Let's see, what can we solve for here? We know two of the three things in the last row, so we can solve for the current. I is equal to V over R, and that would come out to 8.3 amps when you take the 10 volts divided by 1.2 ohms. All right. Next thing, the relationship about voltages in series circuits, or parallel circuits, sorry. You remember we talked about in series circuits, Kirchhoff's voltage law that said whatever potential you gain at the source has to be lost at the load, whatever path you take. So the effect of that here is you need to consider that there's two different paths that the electrons can take. So some of them will go through the first resistor. They start with 10 volts of potential, and then they come back to the source, and they have to be back down to 0 again. They have to lose all their potential at that first resistor, which means that the potential drop across R1 is going to be the whole 10 volts. Similarly, for the ones that they don't go to R1, they go down this branch instead, they have to lose their whole 10 volts at R2. So that's also 10 volts. And this is one of the basic relationships of a simple parallel circuit, is that you have the same voltage throughout. The voltage of the source is equal to the voltage across each load. Now we can find the current through each of the resistors, just using Ohm's law. I is V over R, giving you 5 amps through R1 and 3.3 amps through R2. Now you may notice that the 5 amps plus the 3.3 amps, plus 3.3 equals 8.3 amps. And that's a relationship that you're going to find. This is Kirchhoff's current law. If we were just to draw it here, the total current, so the current through the source, is 8.3 amps. And then according to Kirchhoff's current law, at any junction, whatever it breaks off into has to add up to 8.3. So you've got 5 amps here, 3.3 amps here, and they add up to the 8.3. Notice that more current goes through the smaller resistor, less current goes through the bigger resistor, the path of least resistance, right? And then these rejoin at this junction to become 8.3 amps again. So your relationships here, of course, Ohm's law, as always, applies through every resistor and the circuit as a whole. You get the same voltage across each load as you have at the source. You also know that the currents in the branches have to add up to the total current in the circuit. And then you have this goofy relationship between the resistances, which gives you a smaller overall resistance than the resistors individually. Okay, so given that, let's try one from the textbook. Here we have a parallel circuit with a light bulb and a heating coil. And this is another one where your text likes you to read the question and draw the circuit. This is going to look a lot like the other one, because it's just got two elements. Right. So there's a source. Light bulbs have their own symbol, like that. But really they're a load with a resistance that convert most of the energy to light. This, we don't know the resistance. We'll come back to that. A heating coil just basically is a resistor that gives off a lot of energy as heat. So we'll let the light bulb be R1, the heating coil be R2, your source 45 volts. All right, so the current from the battery is 9.75 amps. That's the total current for the circuit. And 7.5 amps of that passes through the heating coil. So that would be I2. 7.50 amps. And then we're going to find the resistances of the light bulb and the heating coil and the equivalent resistance for the circuit. Now, as always, whatever they ask you to find, just solve for everything in the circuit, set up the chart. Okay, and we'll write in our knowns. And I2. Good. And so now we can immediately fill in a couple of things. First of all, remember the current relationship, that at this junction, the 9.75 amps splits off into two currents that add up to 9.75. So if that one's 7.5, this one has to be 2.25 amps. Okay, so that's Kirchhoff's current law. Also the voltage relationship. By Kirchhoff's voltage law, the 45 volts here has to be equal to the voltage drop across R1 and the voltage drop across R2. So these are 45 volts. And 45 volts. And now we can just apply Ohm's law to each resistor and the series as a whole. So 45 volts divided by 2.25 amps gives you 20 ohms. The next one is 6 ohms. And the last one, 45 divided by 9.75, is 4.62 ohms. And as before, we can run a check on that by using the parallel relationship. 1 over RP should be 1 over 20 ohms plus 1 over 6 ohms. That one, the common denominator doesn't seem so appealing, so you can just throw it into your calculator. Do 1 divided by 20 plus 1 divided by 6, get an answer to that, and then take the reciprocal of it, and that will give you RP equals 4.62 ohms. And so we're pretty confident that we've done this correctly if our check works in the end. All right, so we were asked to find things, the resistances of the light bulb and the heating coil and the equivalent resistance for the circuit. Therefore, here, let's pretend we wrote all these things down. And just go over, again, the relationships here. Okay, so remember, it's all governed by Ohm's law. You've got your voltage the same everywhere in the circuit. And you've got the current in the branches adding up to the total current in the circuit, as well, of course, as our goofy parallel relationship. So that's how parallel circuits work. Good luck.